A basic task of engineering is to assemble mechanisms which make an element move along a prescribed path. Modern electrical engineering allows devices to move with high precision by means of microcontrollers. But many applications still rely on classic methods that use belts, chains, shafts or ball bearings. In this video we focus on mathematical modeling of mechanical engineering. We discuss a new approach that extends the classic way of learning analytic geometry. We use computer algebra for calculation and a LEGO Technic compilation for further experiments. We also show some novel methods in dynamic geometry to study motion linkages. James Watt's parallel motion linkage, invented in 1784, is one of the examples that makes an element moving along a given path, here a straight line. It is still used in the rear axle of some car suspensions, for instance in a 20-year-old Ford Ranger. Watt was very proud of his invention. But unfortunately the center of the short vertical rod moves along just on an approximately straight line segment. The correct motion is a part of a lemniscate that can be described by a sextic polynomial equation, that is, of order 6. A concrete setup is visualized in GeoGebra. The green curve here is a part of the geometric image of the polynomial equation of order 6. In school we learned that an equation of a curve is an algebraic representation of a geometrical object. When all solutions of that equation are plotted in a Cartesian coordinate system, all points of the curve can be obtained. For example, lines are associated with linear equations of x and y, for instance, 2x plus y equals 5. Also circles can be described by quadratic equations like x squared plus y squared equals 4. Also the equation y equals x squared plus 1 depicts a parabola. Higher degree polynomial equations than quadratic ones are rarely discussed in schools. But the idea of defining an arbitrary algebraic curve is actually not difficult. By utilizing GeoGebra one needs to create points A and C, define the segments F and G, draw a circle with center A and radius F, attach a point M on this circle, then draw two other circles with center M and radius G and center C and radius F, and then intersect these circles by defining point F. Finally create the midpoint T of segment MF. When moving M, the trace of point T can be obtained by issuing the GeoGebra command locus T, M. Lastly, the algebraic equation of the movement can be computed by typing locus equation T, M. The curve is eventually extended by some other points. We trust that the software tool reliably computes the equation. That is, the drawn curve is a subset of the algebraic curve being computed. But should we believe that no parts of the Watt curve are completely linear at all? We recall some computations on elementary algebra to prove that no section of a parabola can be linear. We use indirect proof. Let us assume that the parabola y equals x squared has a small linear segment appearing somewhere. The extension of this segment can be expressed as a linear function y equals ax plus b. Since the whole part of the linear segment must overlap the parabola, the equation y equals x squared equals ax plus b must be valid for infinitely many cases. This yields x squared minus ax minus b equals 0 for infinitely many cases. But this is impossible because a quadratic equation has only a finite number of zeros, not just 2 or even less. This contradiction can be applied for other polynomial functions as well. In general, however, a polynomial curve cannot always be written in an explicit form y equals f of x. Even for lines, sometimes it is not possible to express them in an explicit form like that. The easiest example is probably the equation of the y-axis, x equals 0. Also, by using an arbitrary polynomial equation, not just of explicit forms, we can describe multiple curves simultaneously. For example, the implicit equation x times y equals 0 depicts the union of two perpendicular lines. Here the factors of the product x times y, namely x and y, separately define both elements of the union. We can think about them as lines with equations x equals 0 and y equals 0, that is, both axes will appear here at the same time when using x times y equals 0. To generalize the idea, consider the equation 2x plus y minus 5, times x squared plus y squared minus 4, equals 0. This describes the union of a line and a parabola, namely 2x plus y minus 5 and x squared plus y squared minus 4. The union of these two indeed contains an exact line. Clearly, the equation of the union contains a linear factor, even if this fact cannot be easily obtained from the expanded form of the product. It can be proven that a polynomial curve f of x and y equals 0 consists of a line if and only if f contains a linear factor. See Bezout's theorem for details. Let us consider what's linkage again. It is displayed by GeoGebra immediately after computing its implicit algebraic equation, which is a very quick process. In this way, dragging the input points implies immediate change of the displayed curve. After a few experiments, it will turn out that only by modifying the input points, no linear factors will appear. In this way, by doing GeoGebra experiments, we conclude that a 4-bar linkage cannot produce a straight line. Now we will visualize these experiments by utilizing a non-electronic tool. A handy way is to use a LEGO Technic set of beams and connector pegs. LEGO Technic parts are available in many homes, but they can be purchased from internet stores at a moderate price as well. This compilation of LEGO parts consists of 6 kinds of beams, 2 kinds of connector pegs and a pen refill. These parts can be ingredients not only to construct Watt's engine but other linkages, too. Now we will see how an exactly straight line can be constructed with them. Let us start with a simple one. It produces a circle. The red bar is intended to be a fixed part to be held firmly on a sheet of paper by the left hand. The pen refill is to be inserted in the connector peg pin at the end of the white beam. While the red part is fixed, the pen refill will leave its trace on the paper during its movement with the right hand. By using the components of the set, further linkages can be built. For example, Chebyshev's linkage and lambda mechanism also produce an almost straight line. Both curves produce the same sextic, that do not have linear factors. Chebyshev's linkage has a self-collision and can produce 2 disjunct curves. The first one is seemingly straight and the second one is seemingly circular. On the other hand, the lambda mechanism can draw the whole closed curve in one movement. Now let us observe a possible LEGO Technic model on constructing an exactly straight line. We consider Hart's first inversor that was invented by Harry Hart in 1874. It is based on an antiparallelogram. By using computer algebra we can prove that the pen refill moves on a straight line. We can obtain that there is a linear factor of the algebraic curve. It is computed by the locus equation command in GeoGebra. The linear factor, 2x minus 11, is a divisor of a polynomial of 7th degree, that is a solution of an equation system of several equations describing the geometric setup. When assembling this linkage as a LEGO model, it turns out that the remaining polynomial of the 6th degree describes another motion. It is a nonlinear one. It can be realized by pushing the linkage over its extents, changing the antiparallelogram into a parallelogram. Another linkage by Hart is his second inverser that produces a truly straight linear motion, too. This second linkage forms an A-frame. At the end of this video we emphasize that, by using computer algebra, GeoGebra can prove that the motion is truly straight. Also, there is a big difference between approximately and truly straight. To an engineer it can mean the difference between success and failure. And to a car driver between the peaceful error-free use and the annoying regular technical mistakes. By using the computer algebra approach or the LEGO construction, one can study linkages both virtually and physically. These approaches can work together in harmony as a successful combination to connect learners to solving real-life problems, including still unsolved ones.